So welcome everybody. Thank you for joining us today for this Essex seminar series. Today I am excited to have Dr. Christina Karamperidou. Thank you so much. I've tried my best to talk to us about ENSO diversity in past, present, and future climates. Just as a reminder, the seminar is recorded. It will be posted on our YouTube channel in just a couple of days. So I'm going to hand it over to Ralph to introduce our speaker.
Okay, thanks, Kazi. Welcome, Christina. Kazi, try to pronounce your last name. I won't attempt it here since she heard it. But yeah, some of you also heard some of our earlier discussions about ENSOs, and I mentioned how timely this talk is given the fact that we're in a fairly strong ENSO. We've learned that they're not all the same, or the impacts aren't the same. And so I think we're going to learn a bit about that. But quickly, Christina is a civil engineer. In 2012, received her degree from Columbia University. She's now the associate professor and also associate chair of the Department of Atmospheric Science at the University of Hawaii at Manoa. And this is the focus of her research, El Niño-Southern Oscillations and their impacts. And she also recently received an Early Career Scientist Award from IUGG. That was actually this year. And it had to do about the research she does with ENSO. And I think we'll learn a bit about it now. And so I'm going to turn it over to her. So welcome.
All right, thank you very much for inviting me and giving me this opportunity to present this series of studies that I've been involved in the past few years that focus on El Niño-Southern Oscillation and its diversity across climates. And there's many people I'd like to acknowledge. That includes students, PhD students, and mentors and other collaborators. And of course, I'd like to acknowledge support by NSF and by NASA. So I'm going to start with a reminder to everyone that the tropical Pacific plays a key role in modulating global weather and climate at multiple timescales. So at the annual timescale, of course, we have the El Niño-Southern Oscillation with its well-known impacts on precipitation and temperature and everything in between. And at multi-decadal timescales, these sea surface temperature patterns and in the Pacific, whether it be in the form of Pacific decadal variability or even in the form of persistent regimes of ENSO activity, also have global impacts. So in some sense, these gradients or this differential cooling and warming in the east-west sense and the north-south sense, they play a role in distributing energy and moisture to the rest of the planet. So at the centennial timescales, it is important for us to know how they may change in response to external forcing. So for example, in response to greenhouse gas emissions, will we have more of an El Niño-like future, or will we have more of a La Niña-like future? And I think many of you know that this remains an open question. And we turn to models, of course, to answer this question. And I show here from China 2021 the trends in response to high emission scenarios in CMIP5 and CMIP6 models for the meridional SST gradient in the Pacific in the x-axis and the zonal gradient on the y-axis. And as you can see, most of the models project a decrease in both of these gradients. And this would be just fine if we didn't have this problem. And this problem is that now, if we look at the last 40 years or the trends in these gradients, the reanalysis data sets, these three colored dots here, they show a strengthening of both of the gradients, whereas more than half of the models simulate a decrease, a weakening of the gradients in response to the historical forcing. And this has been a very much an active sort of subject of research in the tropical Pacific community to understand and attribute this erroneous warming and weakening of the gradients. And this weakening of the zonal gradient primarily has been attributed, for example, to cold temperature and location biases. What you see here is from CMIP5 and CMIP6 models, the SST and wind bias. This is your cold bias. Also to biases in the equatorial undercurrent, multi-decadal variability, and in our own work, we have related this to biases in simulating ENSO diversity, and I'll talk about this a little bit more later. So, of course, once you have biases and uncertainty with regard to how the mean state of the Pacific might change, then that trickles down into uncertainty on how ENSO might change, because ENSO is impacted by the mean state. But it's also a two-way street. ENSO itself, it impacts the mean state. And for example, via processes like rectification on the mean state. It has been shown, and also theoretically in GIM 1996, that the East Pacific would be colder than it actually is in its mean state today if we didn't have the El Niño-Southern Oscillation phenomenon. So we wanted to look at these changes together, right? The mean state versus the ENSO state change. So this is a plot from our 2017 paper. It's an a la IPCC AR4, if you like, plot, where on the x-axis you have the trend ENSO pattern correlation in each model. So how El Niño-like your changes in the future under high emission scenario versus, compared to how La Niña-like. And then on the y-axis, we have the change in ENSO variance, so stronger versus weaker. And as you can see, most of the models project an increase in the ENSO variance and a weakening of the zonal gradient under strong greenhouse gas forcing. And this holds for the CMIP6 models as well. However, there is a large spread, and this uncertainty is difficult to constrain based on the relatively short instrumental record, especially considering the timescales that we're talking about here. So this motivates looking into past climates to gain some insight into these relationships, and also, to gain some insight in this relationship. And also, of course, if we want to ground truth our models, we do not have data from the past to do, from the future to do that, but we do have data from the past. So this is what we set out to do in this paper with Ali Wyman and Jess Conroy from the University of Illinois. Ali created this new zonal SST gradient in the Pacific reconstruction based on marine sediment proxy records. And this is low temporal resolution records. And you can see that there's periods along the last millennium where you have a weaker gradient and then stronger and weaker again. The color lines here are the HADA-SST and ERSST instrumental period reconstructions. And then we also took a running standard deviation of Nino-3 from a reconstruction of ENSO based on tree ring records. So this now would be a high temporal resolution record. And so these two data sets, the reconstructions, they're independent in terms of temporal scales and also in terms of their the type of proxies they use. And so what we did is that we did this qualitative comparison along the last millennium, looking at periods where the multi-decadal zonal gradient and ENSO variance are uncorrelated or positively correlated. And you can see that these red periods here are the ones where you either have low ENSO activity and strong zonal gradient, or strong ENSO activity and weak zonal gradient. So the two variables are sort of uncorrelated. And in the blue periods, you have them combined together. So a weak ENSO activity and weak gradient, or strong ENSO activity and strong gradient. And you can see that the red periods like dominate, right? And this lends support to that projected zonal SST and ENSO variance relationship, right? That when the gradient is weaker, or you have a Niño-like change, you will have stronger ENSO variance. It doesn't tell us anything about the sign of change, right? It doesn't tell us that the gradient should weaken or not, but just about the relationship. We also went and looked at the past millennium climate simulations in the models, and we did the same thing. We low pass filtered the zonal gradient and took a running standard deviation of Nino-3. We show here the correlation coefficient in this one example And you can see it varies from positive to negative, but mostly it stays negative. This is what is shown here in the histogram as well. It stays negative and statistically significant compared to red noise processes. And this holds for models that best simulate modern tropical Pacific climate, the mean state and ENSO and multi-decadal kind of variability. So these models, they have a more negative zonal SST and ENSO variance relationship in their last millennium simulations. But of course, in general, you can see that there is still multi-decadal fluctuations in the strength and the direction of this relationship, much like we saw with the proxy data. And this could be one of the reasons why now, if we go and look at time slice experiments, which is what we would normally do at first order, right? This zonal SST and ENSO variance relationship remains unclear. So this is here from China again. I show on the left here, Niño-3-4 standard deviation in a set of PMIP3 and PMIP4 experiments for the historical, mid-Holocene, last glacial maximum, last interglacial, and abrupt 4 times CO2. And on the right here, we have the zonal SST gradient in these models, in these same experiments. And you can see that there's no obvious relationship. And partly it could be because, as I said before, you have these multi-decadal fluctuations and you can end up washing out the signal, especially because how negative or positive that correlation is. It really depends on how your model is doing with, mean state and ENSO simulation. But also, it has been shown that subsurface processes may be at odds with the El Niño-La Niña surface paradigm that is really reflected in the zonal SST gradient. It has been shown, previous work on the mid-Holocene, but also in many other people's work for present and future climates and past climates, that stronger air-sea coupling and upwelling feedback due to intensification of the upper ocean stratification in the equatorial Pacific, it leads to increased ENSO variance. And when your zonal gradient is at the top, at odds with that. And there's also processes I mentioned before, like ENSO rectification on the mean state, interbasin relations, extratropical forcings, a lot of things that come into the mix that I show here, like mean SST, and also the annual cycle, changes in the annual cycle of SSTs in the Eastern Pacific. This has been a little bit, less studied, I guess. And that's why in this last chapter of the ENSO in a Changing Climate book that was published 3 years ago, this review and compilation of many studies, we show here the change in the annual cycle in the East Pacific versus ENSO variance change, again, high emission scenario. And there's something there that shows kind of an increase in the magnitude of the annual cycle correlated with an increase in ENSO variance, and that is also consistent with what we've seen in past paleoclimate simulations. So for example, in the mid-Holocene, because of the precessional forcing, we have a weakening of the annual cycle in the East Pacific, and this is related with a weakening as well of ENSO variance. So to summarize, here's this first part of my talk. Most models simulate a weakening of the zonal SST gradient and strengthening of ENSO variance in response to strong greenhouse gas forcing. But we have to take this with a grain of salt because we know that there's biases in these simulations maybe, or at least uncertainty. And but this negative correlation, at least between the multi-decadal zonal gradient and ENSO variance, is supported by last millennium paleoclimate evidence, both data and model simulations. But when you look at time slice experiments, you don't have a clear relationship. And this could be because of multi-decadal variability in this relationship, and also other relevant processes, such as subsurface processes, the annual cycle, etc. And these provide competing influences, not just in the mean state and ENSO, but also when it comes to what we call ENSO diversity, or the flavors of ENSO, Eastern versus Central Pacific ENSO events. So the different processes affect the different events in a competing way in some sense. And in the second part of my talk, I'll try to convince you that to understand the ENSO variance and mean state relationship, I think it's actually very important to understand the ENSO diversity changes, and also have a faithful simulation of ENSO diversity in the models. So back to this original problem, like how will the mean state change and versus how will ENSO change? We said, okay, there's a big spread here. What can we do to kind of make some sense out of this? And we thought that, well, maybe we should separate the models based on how well they simulate this ENSO pattern diversity. And I thought that one simple way of doing this is looking at this, the phase space of the first and the second PC of SST anomalies in the equatorial Pacific. You have this, in observations, you have this boomerang shape, right? And in this boomerang shape means that you can have events along this diagonal, which is the Eastern Pacific ENSO diagonal. In that case, you know, your event is a combination of a positive PC1 and negative PC2. So it would look like this, the Eastern Pacific pattern. And then you also have events on the Central Pacific diagonal, right? So that would be a combination of a positive PC1 and positive PC2. So you end up with something like this. So to reduce all of this in a single number, you can just take the coefficient of the quadratic term of this fit. And we called this the coefficient alpha, which is an ENSO diversity or nonlinearity metric in this phase space, if you like. So then what we did is that we went back to this figure and separated the models into the ones that have a good ENSO diversity versus, you know, weaker ENSO diversity. And we found that this negative correlation between the zonal gradient and ENSO variance and that we saw before, that is also supported by the paleoclimate evidence. It only holds for the models that actually have kind of a good alpha coefficient, if you like, or this boomerang shape. And it doesn't hold for pretty much more than half of the models that don't have this nonlinearity here in the phase space. And importantly, now, if we look at all these three ingredients together, you get something like this, right? So on the x-axis, you have here the coefficient alpha, so stronger diversity versus weaker diversity. This is only for the models that do have reasonable diversity, versus the change in ENSO variance on the y-axis, and on the z-axis, we have the El Niño-like versus La Niña-like change, okay? So what you see from this plane here is that the stronger the simulated ENSO diversity, the weaker the projected Colton warming, so the relative warming of the East versus the West Pacific, and the weaker the change of ENSO variance as well. So in other words, the tropical Pacific is kind of less sensitive to this greenhouse gas forcing if you have strong ENSO diversity. And we made some sense out of this by looking at the what does it mean having stronger ENSO diversity or weaker ENSO diversity? It pretty much reflects this relative importance or contribution of the different feedbacks for these El Nino events. So the models that have strong ENSO diversity, this would be this red bar plots in these different feedbacks. They're pretty okay and close to what we calculate based on observed, right? This is the blue bars. Whereas the models that have a weak ENSO diversity, they specifically underestimate the thermocline feedback and the thermodynamic in the East Pacific. And that is a well-known bias in the models. They underestimate the thermodynamic damping. So then it kind of makes sense that the more you underestimate it, the more you're warming your East Pacific relative to the rest of your Pacific. So the more El Niño-like your change would be. And what I also want to point out here is that when you add everything up, though, say you look at this Barron Stability Index, which would be related to your Nino-34 standard deviation, the models, all of them are pretty okay, right? The standard Nino-34 standard deviation in the models is good. So if you're only looking at that, you're looking at sort of compensating errors that can give you a Nino-34 good standard deviation, but for the wrong reasons. And this is something that has been discussed in the past, that we do have compensating errors when it comes to, in the models, when it comes to ENSO variance. So with this, I think, I'm trying to make the point that looking at how well we're simulating ENSO diversity is very important to get the full story about the changes in the tropical Pacific, mean climate and variability. And because on one hand, the two ENSO flavors, Eastern and Central Pacific events, they respond to different processes. The upwelling and thermocline feedback are very important for Eastern Pacific events, while zonal advection kind of dominates in Central Pacific events. And then if you are trying to use, for example, paleoclimate proxies to understand what happened to ENSO in the past, to increase your robustness of your assessment for what will happen in the future, then the different flavors have different impacts. So you cannot interpret what's happening by only looking at, say, Niño-3-4. The Niño-3-4 box conflates the different ENSO flavors. So you can be missing a lot of the different impacts if you're looking at that only. And to highlight this, I want to talk about this long-standing conflict between Central Pacific proxies and Eastern Pacific proxies of ENSO variants across the Holocene. So a lot of our early understanding for how has ENSO changed in the past has come from lake sediment records in the Far Eastern Pacific, for example, in the Galapagos and in the Ecuadorian Andes. And what these lakes are doing, recording sort of runoff events that have been related with ENSO. And you see that they show that in the early and mid-Holocene, you had a very much muted kind of ENSO-related hydroclimate activity there. And then this has ramped up towards the late Holocene. But when you look at direct SST proxies like corals from the Central Pacific, then what they show is that they show a change in this kind of ENSO-related standard deviation compared to today, but looking across the Holocene kind of goes up and down. You know, it's not really, there's no really an obvious signal of something being very much muted in the early and late Holocene and early and mid Holocene, and then more in the late Holocene. So this has been a long-standing conflict. And back in 2015, we wrote this paper in paleoceanography where we said, well, in order to reconcile these proxies, we really do need to be looking at the Eastern and Central Pacific events, because they have different impacts and they can be on opposite sign in some locations. So looking at the Far Eastern Pacific, you have very wet signal here during Eastern Pacific events. But then in Central Pacific events, kind of in this large scale signal could be neutral or even drying. So you can imagine in a period where you would have a decrease of Central Pacific events and an increase of decrease in Eastern Pacific events and an increase in Central Pacific event, you would get this compounding drying signal that you would see in these proxies in the Pacific, but you wouldn't see them in the Central Pacific. And in our more, in our most recent work, we brought forth a new contender, which is really an old contender, the coastal El Nino events. In these events, you can say it's really the original El Nino. During these events, we had 2023, and now we also are seeing very much of this warming. The warming is concentrated off of the coast of South America, whereas the conditions in the Central Pacific and Western Pacific are neutral or La Nina. And these events typically peak March, April, May. And so I think you see where I'm getting at here, that you can have proxies from the East, from the West Pacific saying, oh, during this period, I had so many La Nina events. And then the proxies from the East Pacific are saying, no, we were getting inundated. This was just strong El Nino events. But that would still be okay, because a lot of these proxies could be recording these coastal El Nino events. And if you're interested in kind of this interplay between these more neutral and La Nina-like conditions and the dynamics of these events, we have this paper with Senzhao, published about a year ago, on the competing effects of winds and La Nina-like conditions in the or La Nina conditions for the evolution of the 2017 extreme event. But I'm not going to go into details for this. I'm going to go back to this, where we wanted to look at now the change in all three ENSO flavors during the Holocene. We did that by looking at time series experiments with CSM1 every 3,000 years. And the box plots here indicate 100-year chunks to assess kind of the internal variability. This is a model that actually has coastal events in it. Many models do not really show the separate coastal events. So in this, what we found is going from the early Holocene to the late Holocene, we have an gradual increase in Eastern Pacific events, a decrease in Central Pacific events, and this sort of step decrease in coastal events. And this is consistent with previous conclusions based on the mid-Holocene, and not just by our studies, but also many others, and also with future projections of increased ENSO variance due to increased stratification. Then, if you're interested in looking at the heat budget and sort of more the dynamical explanation for these changes, I refer you to the paper. And also the higher coastal event frequency in the early Holocene, this is consistent with the La Nina-like mean change. All right, so we were interested in now, based on these changes in the three ENSO flavors, what happens in the Central Pacific and what happens in the Eastern Pacific. So I think, as you can imagine now, if you have the Eastern Pacific events going up and the Central Pacific going down, you kind of like at the zero-sum game when you look at the Central Pacific, Neo 3-4, SST standard deviation, and precipitation standard deviation. So this is what you get in the model. And if you focus in this period that is covered by these coral proxies, you have a step decrease compared to more recent conditions, but then you have kind of like a flat situation here, unchanged. And this is what you see in the proxies as well. But now if you go to the far Eastern Pacific, where we have those lake sediment records, right? The standard deviation of Neo 1-2 total precipitation, which is what the proxies would be presumably recording, right? Looks quite a bit like what the proxies are showing. And this comes partly because you have a decrease in these Eastern Pacific and coastal events together, about 35%, but that's not enough to get this. You also need to have a decrease on their impact on precipitation in the area. So less impactful events. This is shown here by looking at the regression coefficient between the indices for these three types of events and precipitation in the Far Eastern Pacific. So together these, they give you this story, and that is consistent with these lake sediment records. So to summarize, I think this seemingly conflicting paleo-ENSO evidence from the Pacific can be reconciled when considering changes in the relative frequency of all ENSO flavors, not just Eastern Central, but also the coastal event, changes in their impacts, and of course the changes in the background state that are actually related to the changes in the impact. But also, one thing to consider when you're interpreting these proxies is the modulation of these large-scale ENSO signals by regional processes and topography, so the local signals. And this was the subject of this paper with Jill Kiefer, who was a PhD student in my group in 2019. So what Jill did there was to take a weather forecasting model, WRF, to do a dynamical downscaling of the hydroclimate response to ENSO flavors in this area in Ecuador where that Lake Pacacocha is. And this is the elevations, the topography in that area. So she did this dynamical downscaling, and based on these events, she did statistical modeling to quantify the probability of having extremes, which is what the lakes are recording. And then using the relative number of the different events, we can have an assessment of the hydroclimate response in the region. So just quickly here, for the different Andean elevations in that area, we did this generalized Pareto distribution fit to look at what is the probability of having more extreme precipitation or less extreme precipitation depending on what type of event you have. So we can calculate the percentage of exceeding some threshold depending in the high Andean elevations, depending on what type of event you have. And of course, we don't know what threshold needs to be exceeded to get runoff events in the lake. So this is more of like an exercise. This is kind of a moderate shower, 3 millimeters per hour. So having these probabilities, we can go now and look at the simulated number of events in the CSM control simulation And then we can get the expected number of threshold exceeding events in these high ambient elevations, which is what you see here in the black kind of box plot. And on the right here, I have the actual number of events recorded by Lake Pakakocha for that kind of pre-industrial simulation. So these are all consistent and kind of gives our, illustrates this approach that we wanted to give of this hybrid dynamical and statistical modeling of threshold exceeding events to interpret these proxies. And of course, so again, this makes the point that we need to be looking at the different ENSO flavors and not just Niño-3-4. So back to this point, I want to show here, I think this is quite important, on the x-axis. This is from the CSM time slice experiments for the whole Holocene. On the x-axis, I have the number of EP and CP events. So this is kind of the Central Pacific influence events. On the y-axis, I have the number of Eastern Pacific and coastal events. And the colors here are the percentage change of Niño-3 standard deviation. And the blue dots indicate the a percentage decrease that's more than 30%, which is what the proxies in the Central Pacific, the corals, are showing, okay, more than 30% compared to pre-industrial. And so what you see here is that, of course, you can have for the same change, percentage change in Niño-3 standard deviation, vastly different combination of Eastern, Central, and coastal events, which means that your Central Pacific proxies or whatever you're looking at there, Niño-3-4 is saying one thing, and then the proxies from West and East, they're saying another thing, depending on this on this relative contribution. And also, of course, short proxy records. Every tile here is 100-year chunks, right, from all these experiments. Every short proxy records could be sampling any random 100-year period from each of the Holocene time slices. And there's still quite a bit of variability. If you look at the black delineated square tiles here, they are from the pre-industrial control. So there's quite a bit of variability in the relative frequency of these flavors, even within the control experiment with no external forcing. And now you can say, okay, does that help us understand anything about present and future? So what we found is that now, if we look at this basin scale ENSO diversity, like that coefficient alpha I was talking about, versus Niño-3 standard deviation, this colored dots here is from the experiments with CSM1. And this is this positive relationship. And then, of course, and not of course, I'll come back to this. Then this relationship spans actually this relationship in the CIMIP models, these triangles here, the ones that have some sort of the ENSO diversity, that boomerang shape, right? And what does that mean? These are without forcing, right? Pre-industrial control is the triangles. So that means, and this is kind of the follow-up of this paper, that we can possibly draw analogies between past climate changes and model biases in mean climate and ENSO diversity, and constrain kind of this model uncertainty. And if you're thinking that, well, isn't that obvious that you have stronger diversity, you would have stronger ENSO? Isn't that, the case in general? And it's like, not really, because I look at these blue triangles here. You can still have more than half of the models, you can still have strong Niño-3 standard deviation, but not have any flavors. You can have that PC1, varying strongly and have strong events. It doesn't mean that you have that boomerang shape and you have Eastern versus Central Pacific events. This is here CIMIP5 models for reasons of clarity. If you go to the paper, you can see the CIMIP6 models as well. And this holds there too. So the CIMIP6 models, how are they doing with this coefficient alpha? And this is kind of a ranking, if you like, of the models of this coefficient alpha. And I take a pretty lax approach here, whether they fall within this range of alpha coefficient in ERSST and HAD-ISST. And you can see again, well, depending on where you draw the line, right, and how strict you want to be, you probably have about half models. I think they're a little bit better than CIMIP5, but more than half of the models, they do not simulate. They're not within kind of the observed range for this alpha coefficient. And my whole talk so far, right, was based on just saying that this is important both for the projected patterns of SST warming and the projected change in ENSO variance. And in that paper in 2017, we said, well, because this is important for impacts as well. Because, for example, when it comes to hurricane risk, right, and the tropical cyclone formation, it is not only affected by ENSO itself, but also by the relative warming, right, of the storm development region, so the patterns of SST change. So it would be important to use, that's what we said then, to use metrics of ENSO performance to kind of constrain future tropical Pacific patterns and change in ENSO and hurricane risk. So the time has come for us to, we got funding by NSF to work on this with Susana Camargo, Chayin Ling, and Christina Patricola. And I'm just going to use some first results, or I guess from this example. This is the change in the ENSO signal. This is the El Niño minus La Niña signal, the change between historical and high emission scenario for the respective hurricane season in the northern and southern hemisphere for these three ingredients of tropical cyclone genesis, right? The potential intensity, column relative humidity, and vertical wind shear. At the top, we have this for the models that have very strong ENSO diversity, and at the bottom with the models that have weak ENSO diversity. And what you can see, without going into too much detail, I think it's obvious that you can have opposite sign changes here in the model. So then if you put them all together, you end up kind of with maybe washing out the signals. And so I think that this is very important to address and look into, which is the subject of this project. Another example, extratropically now, is this work. This is work done by Madeline McKenna, who is a PhD student in my group, and we have this recent paper in GRL where we look at ENSO impacts on atmospheric blocking. And as you know, atmospheric blocking projections, especially regional, there's quite a bit of uncertainty. It has been associated with the spread in the projected patterns of tropical SST warming in the models. And also we know that El Niño affects these, but the signal is often found to be weak and mostly applies to the blocking formation and not necessarily the occurrence or how strong your frequency is. So this is what you see here. If you're looking at Nino 3-4, right, and you do El Niño events minus climatology, this is the change in frequency that you find, and so the contours is climatology, and the shading is only the significant changes. So blue would be a decrease, and red would be an increase. And we said, much like with everything else I've talked about so far, the proxies, the impacts, all of that, we're probably missing a lot by looking at this. So then Madeline went and looked at the Eastern Pacific and Central Pacific events for, you see here, she did for all the seasons, but here I'm only showing JJA and DJF. And again, much like with the proxies, you can have regions where you have opposite sign signals depending on what type of event you have. And also, for example, in Eastern Pacific events, we see that the center in the Pacific, the center of the blocking kind of action, right, doesn't change, but it's a change in the occurrence there, the frequency. But with Eastern Pacific events, you have kind of this shift in the center, right? So again, we also found differences in the duration of events and intensity and these things that you can look at in the paper if you're interested. So of course, using a single ENSO index like this, it kind of conflates these impacts. And so diversity is crucial, but especially if we're thinking about, the impacts, tropical cyclones, blocking, all of that, it's important to have good forecast skill and be able to differentiate between Eastern and Central Pacific events. But this remains a challenge, even a couple of months ahead for the models. And we also know that, maybe even 3-4 months, 5-6 months ahead, and in past events, the strength of these strong Eastern Pacific events was underestimated or was shown to be more than what it ended up being, like in 2014-15, right? So recently, there's a lot of work coming out using deep learning models to make these long-range forecasts for El Nino and primarily Nino 3-4. But less attention has been paid to diversity. And because of all of the things I talked about so far and how important it is, especially for impacts in the Far East and Pacific and in South America, we set out to focus on ENSO diversity in a deep learning model for sort of medium range predictions, right? We're looking at 12 months here. So this is work by Gerardo Rivera Tello, who is now a PhD student in my group. Previously, he was working at the Geophysical Institute of Peru in Ken Takahashi's group. So what we did here, or Gerardo built this model, which is based, its architecture is very similar to the Hamenal 2019 and 2021 models. But there's some differences. For input, we use 3-month sea surface temperature, sea surface height, zonal wind, and meridional wind. We use sea surface height in contrast to ocean heat content because we want something that is observable, because the intent is to be able to use this to inform operational forecasts for the two types of events. And we get predictions for the E index and the C index, and then a classification output giving us the probability of having an extreme Eastern Pacific El Nino event, so E index being above 1.5 in the following January. Our training strategy here in this version of the model emphasizes extreme Eastern Pacific events. And we also include explainable AI analysis to assess credibility of the of our predictions, because it's important for a forecaster to have a sense of why did the model make this prediction, right? And the model is trained on CMIP data and fine-tuned on reanalysis. And I show here more details you can find in the paper. These are the predictions for the strong 97 and 2015 event. The blue range is the ensemble from our model, and then the orange is from the Nemo model, which is a very good model in forecasting. And what I show here, this is 8-month lead predictions. So this is predictions for based on May initial conditions and February, March, April, May, right? The 3-month. So what I show here is the explainable AI analysis that comes with these predictions, right? So the shading here is the anomalies, the standardized anomalies that actually go into the model. And then the contours are whether the relevance of these anomalies for the prediction of a strong Eastern Pacific event for the classification output. So red is where you actually have a positive, favorable conditions for the prediction, and blue is where you have unfavorable. And it's a good thing to see that what the model is deeming as favorable is what we also know should be favorable, right? This is again 8-month lead, right? The Eastern and Pacific SST and sea surface height, the the westerly wind anomalies, the northerly wind anomalies as well, especially both in the equatorial and the Southeast Pacific and Northeast, in a PMM-like sign, more for the 97 event than the 2015. And in the paper, of course, we thought it was important to attempt this prediction based in May for the current event. So this is initialized in May 2023, which is here, and this is the plume of predictions from the model for the East E index and the C index. And we didn't have anything past May 2023 when we made this. I asked Gerardo, and he put the actual observations up until today here, just to see what the model did. And in the paper we said, well, the prediction here is a slowly decaying E index and a low probability of a strong Eastern Pacific El Nino, meaning above 1.5 in the E index, right? The probability was 52.39. With May initial conditions. And we also cautioned about looking at the neutral values of C because of our training strategy and the samples. And so this is that. And then you can, in the paper we have, of course, the predictions, the XAI, the explanations. And then I wanted to put here the prediction initialized November 2023, so the most recent one from last week, based on preliminary reanalysis, ocean reanalysis data. So these are these predictions. And if you're interested in looking at real time, you can look at it at this website at the Geophysical Institute of Peru. They put out predictions every 15 days or a month. All right. So the one thing that we also found very interesting was that we wanted to relate the skill of the model in predicting these strong Eastern Pacific events with ENSO diversity. So this is now during the development and testing stage before we do any fine tuning. So running the model, testing it on the CIMIP data. We related the critical success index, which is a measure, as again, of model skill for predicting the strong events. We related it with the diversity in the model, that coefficient alpha, right? And you see this, and we found that very interesting. It's not because of the number of events we tested against these. This star here is the observed alpha, right? And so if you want to interpret this in some sense, it says that, well, models with stronger ENSO nonlinearity produce strong Eastern Pacific events that are more predictable. And this ENSO diversity or nonlinearity is a constraint for model skill. So if today the alpha is here, then this is, the model skill you're going to get. And this is consistent with prior work, even Kirman and Scott, for example, 98, but also our work in 2013, where we show that during inactive ENSO periods, when you have strong events, they're less predictable, in contrast to higher predictability when you have active ENSO periods. So this is consistent with what we see here across models, of course, not periods within a model. So I'm going to stop here and summarize my conclusions. I think I kind of beat this to death, that understanding tropical Pacific ENSO climate change and its global impacts requires considering ENSO diversity. And the simulation of ENSO diversity, whether you want to characterize with the coefficient alpha or any other, or your favorite kind of ENSO diversity metric, it can provide constraints to help narrow model uncertainty for the climate change itself in the tropical Pacific, also its impacts, tropical cyclones, atmospheric blocking, and also predictability, and what I just talked about. And models with strong ENSO diversity, they project generally smaller changes, more relative changes. And any changes, of course, in the future will stem from an interaction between the mean climate, ENSO activity, and diversity changes, and the teleconnections. This is what we showed with the Holocene in the models, and that changes may enhance or counteract each other. And I guess my final, pitch here is that now going into the next generation of models, I feel that it's important to incorporate metrics of ENSO diversity beyond just variance for model selection. So if you're looking at your model version, different versions based on the dynamical core, the parameterizations, and saying, well, which one is the one that we put forward? I think that just looking at, okay, does it do ENSO Nino 3-4 standard deviation, right, check. I think that we should look into metrics of ENSO diversity for this selection. And I think I'm going to leave it here and open it up for questions. And thank you again for attending.
Thanks, Christina. So now would be a good time if anyone has a question, go ahead and raise your hand. You should all have the ability to unmute yourself as well. So you can go ahead and ask a question. If you don't have a mic, you can type the question in the chat and I will read it out loud.
I can ask a question. I can't find my unmute button. I can't find the
hear
chat.
you, Mike. I think you're good.
Yeah, hi, this is Mike Evans. Thank you very much for this talk. This was really eye-opening. So I have a number of questions, but I'll just ask what I think is maybe the more interesting one. Do you think, or do you expect diversity to increase as the anthropogenic forcing increases into the 22nd century? And if so, why?
So I think that looking into the, I showed them mid-Holocene Eastern versus Central Pacific events, right? So I think if I had added in that plot kind of a double CO2 or going into the future, it would show an increase in alpha. I think in that model, it's not clear to me. Let me think about it a little bit more. When we wrote the 2017 paper in CIMIP 5 and we looked at alpha, it didn't change much in the models that already have it strong, right? So the models that have it weak, it was increasing. So I think it kind of depends. If you take it just by, I guess, let me go back to this, and I want to, okay, I'm giving you a confusing answer, but I think that, where is this? Not even here. Where is my alpha? Is it this one? I think that even here, it depends on whether you already have a model that can produce the two ENSO flavors, and then it would show smaller changes in this relative frequency of the events, or you have a model that does not get this right. I think that China, for example, in 2018, they separated the models based on this coefficient alpha, and they looked at the better ones, and then there they showed stronger more Eastern Pacific events. It doesn't mean that the curvature would change though. So alpha could still remain the same, you know, because of the way that alpha is constructed. So I guess it depends on what you mean by would ENSO diversity increase, because the coefficient might not increase. The relative frequency might increase, but I'm not really, I guess maybe. The idea here is the same as with the going from the mid-Holocene to today, right? We showed that here, that the reason why you have more Eastern Pacific events is because you have an increase in the upper ocean stratification, which is what has been shown for the future as well. So you have a weaker gradient, but an increase in the upper ocean stratification. That gives you more Eastern Pacific events. So in that sense, I would say that, yeah, diversity will increase if you define it as having more Eastern Pacific relative to Central Pacific events. So I think I took the cynic route to answer your question, but.
Yeah, thank you. That was great. I'd love to hear how you were thinking about it.
But I think the other, I guess I want to mention this, the silver lining, you can say, right, is actually, when I talked about the model here, let me go to the last slide here, okay? So the silver lining of this, right, is that if this is true, that, and so, that if you have stronger diversity, right? This is flipped here because it's negative, but stronger diversity is on this side, okay? So if you have stronger diversity, then you have better predictive skill in this model, and presumably, you know, other models as well, right? Then, again, the silver lining is that if you, in the future, if this observed, you know, ticks up, then your predictability or prediction skill also becomes better. So you may have stronger events, but then you're able to better predict them. And that is important for anticipating and mitigating the impacts, right? So this is kind of I think the silver lining here.
But is that only true for this deep learning model, which might be rewarded for picking out, you know, the peculiarities of individual events, versus, say, like finding that in, say, the output of an intermediate complexity model that's, you know, run for the same amount of time in events?
Right. So of course this is right. As I said before, we kind of checked against maybe this is an artifact of the number of events and the samples, etc. It's not, but of course, yeah, this is specific to this event, but to this one. But I think that what we've saw, so for example, the 2013 paper, we looked at multi-decadal variations in ENSO predictability using a time series based, this is locally Lyapunov exponents, so it's a time series dynamical systems theory based assessment of predictability. And we actually confirmed what the Lyapunov exponents were saying against reforecast experiments. This was with GFDL's CM 2.1 model. And so we did find the same thing there, that when you have periods of weaker ENSO activity, right, you would still have strong events, and those strong events were less predictable than in the case where you have stronger activity. The events embedded in a stronger activity period were more predictable. And I think others have shown these as well. That's why I mentioned Kipman and Skop 1998. So I think even though this event is indeed based on this model, obviously, that is geared towards these strong Eastern events, I think there's other studies that agree with this. So I think that, you know, it might be true, right? I mean, we live here, we're kind of living in the model world, so.
Yeah, it seems, I follow your reasoning. It seems a little just counterintuitive that something that was, you know, more, had more flavors would be more predictable. I think, like, you know, a simpler pattern should, all else equal, be simpler to predict.
But I feel that but I guess how it makes sense in my mind is that when you have, you know, a very weak period and not too much, and mainly you have one type, and then suddenly you get this strong Eastern Pacific event, that's difficult to predict. Whereas if you have this pattern, if you are kind of, if you have this more diversity, then I don't know. I mean, I guess I don't know why it makes sense in my mind. It's more of an outlier. And I guess it would be very true for this model, especially, right? The machine learning model. That
maybe you have more different patterns to train on. And so you can, you know, recognize in validation something unusual, as opposed to if everything looks like an orange, you're not going to see it. You're not going to see an apple.
and I think that that's why it's nice that if you go to the either the paper or and then the website, we always put out the XAI, we use layer-wise relevance propagation here, because it's important to look at that, because that informs kind of, that can help you make this kind of inferences that we were just talking about, right? We saw in the paper also a case of a false positive in the model. And you can see very clearly that based on the relevance patterns, the model shouldn't have predicted a false positive, but it did. But then once you have those relevance patterns, then as a forecaster, you can say, you know, this looks a little odd, so I'm not going to put that much weight in this forecast. But we need to have this, because otherwise we cannot just, not just this model, but any model, we cannot blindly believe what the model says unless we have a sense of whether what it says is consistent with our understanding of the dynamics and the evolution of these events. Thank you. I hope we're not hogging all the time. Someone else should ask a question.
Are there any questions just before we conclude today?
I have another one, but totally defer to somebody else.
Let's give it like a 15 seconds, see if somebody wants to raise their hands. Mike, go ahead. Oh, wait, Ralph, do you have a question? I just saw you unmuted.
I just want to say thank you, Christina, for a great seminar.
Thank you so much.
Mike, you can go ahead, I think, and then we'll just wrap up.
Okay, thank you for taking one last question. So I'm thinking about the process of doing what we call climate field reconstruction from sparse observational networks of paleoclimate observations. And it's also kind of relevant for the process of paleoclimate data assimilation. You're probably familiar with both of these things. Tell me, what do you think are the implications for ignoring ENSO diversity for both of those endeavors?
So I think, so the offline assimilation, right? I think, you use different GCMs to get your patterns. I would think that it would be interesting to see if there's a difference if you subselect the models based on, say, their coefficient alpha or how they're doing diversity. You can look at the patterns. You don't have to do, I mean, I'm partial to this coefficient because I thought it was like a nice, easy way of doing this. But I think that it would be interesting to see, right? If you have different, and I'm not really, sure if what I'm saying makes sense, but you do put out an ensemble, right, of the reconstruction coming from using the patterns from the different models. And I feel that it would be a nice exercise to see how different are the results if you take the models that actually have the ENSO flavors based on the ones that don't have. Because I think it's obvious, right, that the impacts are different. So if you're based on teleconnections to do this reconstruction, so there must be a difference there if you're using models that actually are simulating the diversity and the consequent or the teleconnections or even the impacts in the Pacific, right, versus the ones that are not doing that right. Does that make sense what I'm saying?
Yeah, that totally makes sense. And from the observational side, probably you need to restrict your observations to telling you only about very localized phenomena. Otherwise, you might be, projecting central equatorial Pacific ENSO onto eastern equatorial Pacific when it has, no right to be there.
Right. So I think that's something that is quite interesting to look at. I'm now curious to see if how different their construction would be.
Yeah, it sounds like a pseudo proxy experiment, and I would probably start by looking to see whether Wang et al. 2014, which looked at a lot of these different questions, but I don't know if it looked at locality and subselection of or comparison of different models for the prior. Would have looked at that, but I think Smerdon et al. 2011 did for just two different models, and the results were different, which suggests that you're right.
Yeah, the question I guess would be if they're different but kind of similarly different based on this metric, or it's just that they're different and you cannot constrain it based on. I would think that you should be able to constrain based on ENSO diversity, because this is kind of like the point, like that's what you're trying to reconstruct, right? So yeah, I think that would be interesting to swap the priors, do some sort of like kind of this type of analysis. And also, the coastal events, I think, are important. They're very rare, though. Well, we thought they were rare until we had the 2017 and then in 2023, and then so anyways. But
the appearance of diversity. Well, thank you again for a great seminar and for answering all these questions.
Thank you, Mike, for your questions, and thank you, everyone.
Yes, thanks everybody for coming, and thank you so much to Christina for coming giving us this great talk today. This video of the seminar will be on our YouTube channel in a couple of days, maybe a week. And I also just want to encourage everybody. We have an in-person seminar on Wednesday. It's our last in-person of the semester. It's at an odd time. It's noon, so it's different for us. But yeah, so if everyone can come to that, that would be great. But other than that, thank you, everybody. Have a great afternoon.
Thank you.
Well, have a good afternoon.